All right, we're going to look at 2734. So it says a 4 kilogram mass. Why do I write down my given? Because when I write that the mass is 4 kilograms, if they happen to give me grams and I write it down and I see it, then I might say, oh, I need to convert that. So it's important to write everything down. And again, we're going to chunk and write as we read. It starts from rest, so VI is 0. It slides along the surface as shown in the diagram. The incline has a coefficient of kinetic friction, so mu sub k is equal to 0.20. All other surfaces are frictionless. When it reaches the end of the track, it runs into and compresses a spring of maximum distance. So you see now when I write x is equal to 12 centimeters, when my hand writes cm, I'm going to say to myself, it's not centimeters, it needs to be meters. So 1, 2, so this is 0.12 meters. So then I won't forget to do that at the end. It compresses a spring of maximum distance. Determine the spring constant. So I want to find K. I'm not just writing equations down. You don't learn physics by writing equations. What we're going to do is we're going to look at this picture and holistically we're going to say what's happening in this picture. So when I look up here at the top, this block is at rest. If it's at rest, it means what? It doesn't have any kinetic energy. There's no spring there, so in the beginning, this is all gravitational potential energy, MGH. Now it's going to, at the end, it's going to be here. At the end, it's going to compress the spring. So there's going to be potential energy stored in the spring, 1/2 kx squared. Now, it's going to come to rest at the end when the spring is completely compressed. So there's no kinetic energy again. But again, as far as gravitational potential energy, I have to look at my frame of reference. So what I'm going to do is I'm just going to draw on here a line showing this is what I'm calling my base level. So this is where I start at the top. So at the top, I'm going to call this H naught. That's my initial height. Now at the end, I'm going to have the height here, and I'll call this HF. Remember, I determine what I'm calling my frame of reference. In physics, you cannot do physics without a frame of reference. So my frame of reference is down here. Okay? So, in order to get full credit, what I have to do is I have to write some kind of statement about conservation of energy. Now, in layman terms, I might say the total energy here is equal to the total energy here. The problem is, it's not a problem, but I need to know that there's work done by the frictional force when the block moves up this incline. So when I write my statement, I'm going to say K naught plus UG naught, this is the gravitational potential energy, plus USO naught, minus the work done by friction is equal to KF plus UGF plus USF. So this is a statement saying conservation of energy. Now what I might do first is I might say, okay, this is right here at the top, right? So at the top, I know that it's at rest, so the kinetic energy is 0. I know that the spring isn't compressed, so that goes to 0. And at the end, it comes to rest when the spring is compressed, so this also goes to 0. Now I'm going to substitute in my values. So this is going to be my gravitational potential energy at the top is going to be mgh naught. The work done by friction, remember work is equal to FD, so it's going to be the frictional force times that displacement, and that's equal to mgHF plus 1/2 kx squared. Now we're solving for K. Now, somewhere on our FRQ, they're gonna say you're gonna get 1 point for a statement showing conservation of energy. Now, are we sure? Are they gonna show it like this, or are they gonna show it like this? We're not sure what the rubrics looks like, so we're gonna write both. Why are we gonna write both? This way we're guaranteed to get that point, because we want that point just showing conservation of energy. If I don't write this, I don't get that point. So I'm going to write it both ways because I don't know what the rubrics looks like. All right, now, even though they gave us all these numbers in here, we're not just plugging in numbers. Because what if now we have one where we have to rearrange the equation? What if there was no numbers here and this was just m, v naught, mu sub k and x, and they wanted my answer in terms of variables. So that's why we're going to rearrange the equation to solve for the unknown in terms of the known to practice doing this. So if I do this step by step, so I have mg h naught minus, well, I know f of f is mu times f of n. Why am I doing this? Because if someone is grading this, they need to follow what I need to do. So if there's a point that says, well, you need to say f of f is mu times f of n, can they see that in my work? That I know that mu is equal to f of n? Yes. So that's equal to mghf plus 1/2 kx squared. Now, what is f of n? F of n is not that simple. Remember, this is on an incline. I don't do stuff in my head. They didn't ask me to draw a free body diagram, but I want to picture this. So if I draw a small sketch to the side to help me, I know the block is moving up the incline. I know that if it's moving up the incline, the frictional force acts this way. The normal force is perpendicular to the surfaces in contact, and my weight acts straight down. Now, what I need to do is I need to break my weight up into its components. So I'm drawing it another color so you see this is FGY and this is FGX. And this is my angle theta. So now if I was to sum forces vertically, and I don't have to show this work, but by me drawing a diagram I see it clearly and I don't make a mistake. And if I sum forces in the vertical direction, which it's not accelerating in, we can see that Fn is equal to Fgy, so Fn is equal to mg cosine theta. How do I know it's cosine? Because it's adjacent to the given angle. So now in my work here, I'm going to say mg h naught minus mu. Instead of f of n, I'm going to write mg cosine theta times d is equal to mghf plus 1/2 kx squared. So what I'm going to do now is I'm going to try and isolate k all by itself on the right hand, because I'm going to substitute my values at the end before I start plugging stuff in. Okay. So now what I'll do is I'll multiply both sides by 2. So I'll have 2 mg h naught minus mu mg cosine theta times d. I'm going to move this to the other side, minus mghf. Then I'll divide by x squared is equal to k. I can pull out the mg, make it a little bit easier. So now I can say 2 mg h naught minus mu cosine theta times d minus hf over x squared is equal to k. So if they asked me to solve for the Spring's constant in terms of mg, the different heights, if they gave me the heights, and theta and x, I am now not just plugging numbers in, because a lot of times now you're asked to do it in terms of given variables. Okay. Now, before I start plugging these numbers in, I need to look at my picture up there. What I see is I have this 2.6. That's the frictional forces moving. What I don't know is I don't know HF. So in my given, I'm going to write that H naught is equal to, they showed me the radius of this circle, so this is 4.8. But in order to find HF, that's this height. So this is my right triangle. I have the hypotenuse and I have the angle, so I can say that HF is equal to 2.6 sine of 30 degrees. So HF is equal to 1.3 meters. Okay. So now I can go ahead and I can substitute that in, and I can say 2 times 4.8 times 9.8 parentheses 4.8 minus 0.2 times the cosine of 30 degrees times 2.6 minus 1.3, have to be careful there with my parentheses, divided by 0.12 squared. When you do algebra on your calculator, that's how you make mistakes. So when I do all this, K comes out to be 19925 newtons per meter. And that's not in correct significant figures, but we want to know how to do the physics. So again, when I look at the problem, I'm not just saying, oh, what numbers am I putting in my calculator, what equations am I using? I'm saying, what am I doing? I'm saying I'm using conservation of energy. And I see that there's work done by friction. And that's it.